Okay, it's time to begin. Today, we're going to begin with the citation review of the test first. And then after we finish that, we'll go to the extra problems that I gave you through Blackboard the other day. So that's kind of the sequence that we're going to do things today. Okay, on the test, there are 30 questions. The problems. Number one, I give you a set of ordered pairs. Okay, then I ask you to write a set of ordered pairs that are the inverse. The citation for this is section 4.1.0, page 409, problem number 1. Problem number 2. I ask you a question about the definition of inverse and as it comes to graphs. Page 409, problems 1 and 2, and the same section citation. Number 3 is from 4.1.1, and on it, the instructions for both problem number 3 and 4, which have the same citation, are determined if the relation defines y as a one-to-one function of x. I give you a graph of an equation, okay? And then based on that graph, you have to tell me if it's a one-to-one. And of course, you want to use the horizontal line test on that to determine it. The citation is page 410, problems 13 through 22. Number 4 has the same citation and is the same type of problem. Okay, number 5, the general instructions are determine whether the two functions are inverses. And this time you have to do it algebraically instead of graphically. So basically you're going to have to use the compose function and see if you compose f compose g, if you get 1x, and g compose x or f, and see if you get 1x again. And if you get 1x on both answers, then they are inverses. Your citation for problem number 5 is 4.1.2, page 411, number 31 through 36. Problem number 6, I give you an f of x value and you have to find the inverse. You use the 4-step method, okay? What are those 4 steps? Change f of x to y, then interchange the x's and y's, isolate the y, and then finally use the f inverse of x notation. The citation for problem number 6 is 4.1.3. The page numbers are 411, number 41, and page 412, number 67 through 68. Problem number 7, I give you a function and I tell you it is a one-to-one function. And what you have to do is find the inverse, again, using the 4-step method. Citation 4.1.3 again, page 411, problems 41 through 52. Problem number 8, same general type problem, except it involves a cubic, and the citation, the chapter is the same. The citation is page 411, number 45 through 46. Problem number 12. Okay. Given that the domain of a one-to-one function f is a certain interval and the range is a certain interval, then you have to state the domain and range of its inverse. On number 9, the citation is 4.1.3, and the page and problems are 411, 412, number 53 through 60. Problem number 10. I give you a graph of a function and you have to graph its inverse. Now, you can do it the hard way, or you can use that shortcut trick that I showed you, graphing the function, finding points on it, and then interchanging the points. The citation for number 10, 4.1.4, and page 412, number 71 through 74. Now, the reason that I'm giving you these chapter citations today is because the second half of today and tomorrow, when we're going over those word problems that I gave you, that I sent you on Blackboard, at the beginning of each one of these, it tells you out of which section it is. So you can kind of correlate this with the type of problems you see there, as well as what I give you for problem numbers out of the text. Okay, problem number 11, evaluate the function at the given value of x. In other words, I'm going to give you a substitution value for x, and then you round it off if necessary. So you will need your calculator for this particular problem. The citation on that one is 4.2.2. This is an exponential function that I'm giving you. It could be with e, or it might not be with e. It might just be with numbers and variables. At any rate, I do give you a substitution value, and you have to find the overall value. Okay, page 424, number 37 and 38. Problem 11, excuse me, number 12. Number 12 is a multiple step word problem. It involves principal, interest, time, and you have to do a simple interest computation, and you have to do a continuous interest computation. So you need to know those 3 interest formulas and which one goes with which. Your citation for number 12 is 4.2.3, and page 424, number 45 through 52. You'll need a calculator on that problem. Number 13. Number 13 is a multiple choice. It says graph the function and write the domain and range in interval notation. So in other words, I give you a function, and then you have to tell me which of the 4 choices is the correct one with the correct domains and ranges. The citation for number 13 is 4.2.1, and page 423, number 15 through 22. Number 14, use the graph of a function that I give you to graph the following. Then you also have to write the domain and range in interval notation. Okay, so I give you a function, it's an exponential function, and then you have to graph it and give the domain and range. The citation for number 14 is 4.2.1 again, and page 423, problems 23 through 32. 23 through 32. Problem number 15. I give you an exponential function. And what I'm really wanting you to do is understand transformations on exponential functions that you graph. It's a multiple choice graphing problem. So what you've got to do then is you've got to figure out what would be the original graph and then what would be the graph after you apply the transformation that they dictate. The citation is 4.2.2 and page 424, number 39 through 44. Problem 16. I give you a logarithmic equation and you have to convert it to exponential. That's 4.3.1, page 434, number 9 through 16. We're going to have to wait on my clock. Nope, that was the 45-minute chime. Problem number 17. Again, I give you an exponential equation, or not again, but I give you an exponential equation, and you have to convert it to logarithmic. Okay, the citation for number 17, 4.3.1, page 438, numbers 17 through 24. Number 19 has the same citation. I'm giving you our 18 and 19. Number 18, I give you a logarithmic. You convert it to exponential, okay, and you solve it or simplify it. On 18, 19, and 20, the citation is 4.3.2 and 4.3.2 and 4.3.3. And the page numbers for all three problems, 18 through 20, are 438, numbers 25 through 50. Number 21, it says use the product property of logarithms to write the logarithm as a sum of logarithms. In other words, you are expanding a single logarithm. The citation for 21 is 4.4.1, page 450, numbers 7 through 12. Okay, problem number 23 is a similar problem. I'm going to tell you it's going to be a difference of logarithms using the quotient or the division property. The citation for that is still 4.4.1, page 450, now number 13 through 18. I hear my neighbor's obnoxious dogs barking. My dogs don't bark much, fortunately. Okay, number 23. Write the logarithm as the sum or difference of logarithms. Simplify each term as much as possible. In other words, I'm giving you a logarithm, and you may have to use additions or subtractions depending on whether it's multiplications or divisions. You also will have to use what I call the power rule, dealing with logarithm exponents. So you'll have to simplify that. This applies to problem number 23 and problem 24. The citation for 23 and 24 is 4.4.2, and the page numbers are page 450, number 25 through 36. Problem number 25, I give you a logarithmic expression that's expanded, and you need to contract it back to a single logarithm. In other words, you're using these properties backwards. The citation for 25 is 4.3.3, and the page is 451, problems 45 through 56. Now, that could be a natural log or it could be a regular log. Problem 25, I also give you a problem that requires change of base. Now, yes, I've told you you can use your calculator to figure these out. However, what I expect you to do on this one, and this is key, give your answers in terms of E. That means you're still going to leave it in natural log format. You're not going to give me a number that you would get out of a calculator. So you've got to demonstrate to me that you understand how to use the change of base formula. Okay, the citation on number 26 is 4.4.4, page 451, problem 79B, and page 448, paragraph 4, or example 4. Now, number 27, I give you an exponential equation. We've moved from expressions now to equations. Write the solution set with the exact solutions. Give the approximate solutions to 4 decimals if necessary. Okay, so on these, number 27, the citation is 4.5.4. And with that, you've got page 462, problems 5 through 16. That is the same citation for number 28. In this, you're going to have non-compatible bases, so you're going to have to do some logarithmic tricks, or you could have compatible bases where you're able to convert one base to the same as the other and simplify it. We've done a number of examples of these type problems. Problem 29, I give you a logarithmic equation and you have to solve it. Number 30 also is a logarithmic equation, multi-step, that you will have to solve. In both cases, you will have to check and make sure that none of the solutions you get are undefined. So the citation for number 29 and 30 is 4.5.2. The page is 463. And the problem numbers are 37 through 56. So that's the citations for the test. Any questions before we transition to the next activity? Okay. The next activity we're going to take is we're going to begin going over those problems that I gave to you on Blackboard. Hopefully you copied them and have been working on those. You know, if you don't have it correct, correct it as we go. We're not taking a grade on these. Now, we're going to do that the rest of today. And then tomorrow, we'll finish what we don't get done today. Plus, we're going to work on about 10 additional logarithm and exponential practice problems to help you get better ready for the test on Wednesday. Since some of you are here that weren't here earlier, I'll restate for the test on Wednesday. You may get there as early as 11. We're probably going to have to shut down about 12:15 because of an incoming class. All right, so let me turn on my share screen and get the sheet that we need to be going over. Okay, it looks like this. And so we'll start going over that. At some point, I may need to get out my calculator, and if I do, I will. Okay, here we go. A set of coordinates. Find the inverses. Well, in this case, they're just asking you, is it 1-to-1, yes or no? Okay, you'll have to remember, in this case, you've got a different x or a different y for every x, or a different x for every y. Now, problem 1 on the test, I give you something like this, and you have to tell me the inverse of it. Okay, problem number 2, you have to see if these are 1-to-1 or not. Number 3, you're using the horizontal line test. This is similar to your problems 3 and 4 on the test. Number 6, you're determining whether it's 1-to-1. Now, they're just using the A equals B, A is different to B test in this case. I don't actually have a problem on the chapter test that uses this particular skill. Okay, on this, now this is very similar to what you're going to have on problem number 5. Here are the rules that you've got to deal with, where I said the composition one way equals x, the composition the other way equals x. Remember, this means you're taking the g equation and substituting into x. This means you're taking the f equation and substitute it into g. And here are the 2 problem sets. This is very similar to problem number 5. These 2 are. Notice here, we got 1x for the f compose g, so we have to check g compose f. And in this case, we got 1x again. We're done. Over here, we did not get 1x. We got 5x plus 2 over 5. If you don't get 1x on the f compose g, there's no point in doing the g compose f because they will not be inverses. So you can just stop if you find that it's not equal to 1x. Now, there are some people who would disagree with me and think you ought to do it anyway, but I believe in working smarter, not harder for Carter. Okay, the next one, the 4 steps for finding an inverse. Okay. If we look at problem number 10 here is very similar to problems 6, 7, and 8 on the test. Except on 6, 7, 8, you don't have to graph it. But you do need to know, you can see this diagonal line that potentially could be through here, okay? You do need to know that inverses will be a reflection across that diagonal y equals x line, okay? I don't know if my pen will let me draw that or not while we're in this. Uh-oh, it doesn't like that. Try one more time. Okay, this is the line y equals x. Okay. Okay, here's number 11 is another one where you go through the 4 steps. First, you change f of x to y. Then you interchange the x's and the y's. Then you isolate the y. And then you put the inverse notation back in again. And now we are going to have to wait on my clock. Now, although you're not going to have to graph mine, they did graph these, okay? The blue lines would be what this would be composed of. The red lines then in turn would be the inverses. Actually, I said that backwards. Okay, here would be your first one, and then it would be your inverses. Notice these reflect across that y equal x line again, okay? This is a mirror of that. These two are mirrors of each other across the y equal x line. They also, in this example, use the checked to see if by composition it worked out, and yes, it did. You're not going to have a problem that difficult on my test. Here's one where we've got a quadratic, but they put a limitation on it, okay? In other words, what we're talking about is half of a quadrilateral here. So in other words, this would come up like that, and this would come out like that. But we put this limitation on it so that we don't get a, when we deal with this square root, we don't want to get a negative value, okay? And also, the main reason we do it is if we don't limit this thing, then it would not pass the horizontal line test, okay? This side would pass, but that side would not. But this one would not pass the function test. Okay. I give you the blue values you've got to graph the inverse. That would be these red values based on this column right here. Okay. This is the primary, that's the inverse. Notice they reflect across the y equals x line. So in other words, if this is f of x, then this is f inverse of x. Okay, exponential functions. Okay, here are just examples of them. In this first example, we're graphing it here. I did not have you graph any exponential functions that I recall, although I gave you a graph of one and you had to deal with it, with a transformation. Okay. Remember, if I replace this x with negative x, it's going to flip it across the x-axis like so. I said that backwards. If I replace this x with negative x, it'll flip it across the y-axis. If I have a negative in front of the 3, then it'll flip it across the x-axis. I said that just backwards, my apologies. Why is that the case? Because 2 to the negative x can also be expressed as 1/2 to the x. Now, if you have a fractional exponent, you can expect it to go downhill left to right. If you have a whole number exponent, then you can expect it to go uphill left to right, or a positive exponent. Okay, in this case, we got three transformations. We're going to move one place to the right, one place to the left, because it's opposite of sign. Then we're going to flip it across the x-axis upside down, and then we're going to raise that upside down up one place. So in other words, you see right here, this was here, it would have been like that, with the blue line here at -4, but then we moved it up one. Notice your scale goes by 2s on the vertical scale. Okay, here's the parent function in red. Your transformations, first of all, the x plus 1 shifts this one place to the left. Then the negative reflects across the x-axis. And then the plus 1 goes up 1. So you are asked to say, what changes would it make? Well, I went 1 to the left, 1 up, and flip across the x-axis. And again, here's in generic terms what you do. I'll leave that there for a moment if you want to make notes. Okay, when we talk about E, you need to know the first 4 values of E, although you are going to be allowed to use your calculator. In this case, we're just putting in the values of E using the calculator. Let me share the calculator. Whoops, what did I do? I did the wrong thing. Let me bring this back. Then let me bring this forward. So I've got them both open. Okay, this first problem, e to the second. Okay, so we use the alpha e right down here. Now, since it's second, we could use the x squared, or we can use the x to any power, put in the 2, and it's always good to get out of the power and before you hit the equal sign. And there's a hidden 7 right here. Okay, problem number 5. In this case, since I use the any power, I can very easily delete that 2 and put in a -3 equals. Now I want square root of 7 power. Well, I move it back up there again. I delete the -3 and I hit square root of 7. Get it out of the power, equals. Now I go to e to the pi. So I'm going to get it back up there, delete out this power. And now I've got to put pi in there. So I've got to find my pi key right here. Now, before we use the alpha with the e, this time we're just going to use the shift key with the pi. Get it out of it, equals, like so. Okay. Next problem, I'm going to scoot this over kind of out of the way. I can drag it back if I need to. They want you to graph f of e plus 1. Okay, in this case, here is your basic graph. And by +1, okay, e plus 1, that means it's going to shift it one place to the left. So instead of this point being at 0, 1, which would normally be the anchor point on this for e to the x, we're shifting it one place to the left. Notice I've got a by 2 scale up and down and a by 1 scale left and right. I prefer not to do that, but you can. Okay, here are your 3 interest formulas. You need to know all 3 of these, and you need to know when to use them. If you're going to do simple interest, you'll just use the principal amount, the rate, change to a decimal, times the time. And that'll give you the interest for that 1 year. Now, if it's multiple years, simple interest, it's still just one computation. Now, if they do it periodically, for example, semi-annually, quarterly, whatever, the n is how many times a year that you're computing it, both here and here. Your interest rate changed to a decimal, and then your time in however many years, and that gives you the total ending amount. Here, for continuous interest, your principal, the rate, and the time, okay? And that gives you your ending amount and that number of years. Now, you're gonna have to know those for problem number 12. Number 12, we've got some problems like this, okay? Here, we're compounding annually or once a year. So we use this formula. You can see the substitution. You plug all of this into your calculator, being careful to put in the parentheses. You'd put this stuff in this parentheses, then you would hit the x to the power key and then put in the 7 and you would get this, which you'd have to round off to the nearest penny. Compounded quarterly, instead of using n equals 1, then you would have to use n equals 4. So you put these in, 4 times 7 is 28. I mean, you could put 4 times 7 in the power box, but I wouldn't. I'd just go ahead and do it in my head. And then you get this as a difference. Over here is compounded continuously. You put the 1,500 in, you put the rate in times the years. Okay, how are you going to do this in your calculator? You're going to put this number in. Then you're going to use the alpha E key, then the x to the power key, and then you're going to put 0.025 times 7 for the power key. And then get out of it and equals. So that'll be like your number 12. Problem number 10 here. Again, they're having you do a problem. You're not going to have a problem like this one. Actually, I thought I marked this one where you didn't have to do this one.
Professor Carter?
Yes.
The screen is frozen.
My screen is frozen?
Yes.
You're not seeing the movements?
No. I'm only seeing the calculator.
Okay. What about now?
No. It's stuck.
What about anybody else?
I can't see either.
What? You don't see movement?
See either. No.
Okay, let me stop all screen sharing and re-screen share. Now do you see it move?
Yes, sir.
Okay, thank you for letting me know.
No problem.
Okay, did you see this screen before I moved on?
No.
Okay, these are problems similar to number 12 on your test, where you can use the simple interest formula, the compounded formula, or the continuous formula. Okay, here, we're not going to have a problem like the number 10 and 11 here. Okay. So we're going to go on to these logarithmic functions. Here you're changing to exponential form. Remember, base remains base. This becomes your power. The argument becomes the solution. Base stays the same. Your power here and the argument. Remember, the argument also can never be negative, a negative value. Okay, base stays the same. Anything to the 0 power is 1. So in other words, a log, anything to 1, argument of 1, the answer is going to be 0, or ultimately the answer will be 1. Here, anything to the 1 will give you the 0 power. Write each solution in logarithmic. Here we're going just the opposite. We're changing exponential to logarithmic. Base stays the same. This becomes your argument. That becomes your solution in all 3 cases. Now, those are similar to what you might encounter on problems. Let me see if I can find them quickly. Beginning with number 17. Okay. These problems would begin with number 17 on your test. Now, evaluating, I'm not going to put the calculator on because I don't want to freeze my screen again. I don't know why it did it today when it did not do it the other day. But basically, you know, you're going to work these out. You're going to take this, you're going to change it into exponential. In this case, you don't even need a calculator. 12 to what power is 144? Well, it's the second power. 64 to what power is 8? Well, the square root of 64 is 8. So the 1/2 power. Okay. 3 to what power is 1/27? Well, 3 to the -3 power is 1/27 because the negative makes it 1/, and 3 to the 3rd is 27. Okay, now we're going the other way, starting with logs that you solve. Okay, if you're just given a log of 100, you change it to exponential, and 10 to the second is 100. So 2 is your answer on this. Okay, log of 10 thousandths. Well, 10 to what power is 10 thousandths? It's -4. You can also get these using your calculator very easily. And I've gone over problems with that multiple times. These you would have to have a calculator to do, okay? And you put in log of 200 and it'll just give you the answer. If you want to do it mechanically, you can do it this way and it'll work out real close approximately. Remember, if you've got a rounded off answer, you have to use the approximate symbol. Remember these basics. B of 1 always equals 0. B of B always equals 1. Okay, whether it's B of B this way or B of B that way. Okay, B of X to the X, I should say, is X because the B of B part is equal to 1. Okay, now, in these problems, log 19 of 19 is 1. Log 10 of 10, there's a hidden base 10 there, is going to be 1. Natural log of E is the same thing as regular log base E of E, so it's 1. Any base of 1 equals 0 because any base to the 0 power equals 1. Okay, again, any base of 1 equals 0. Any base of itself gives you 1 to the 10th, or excuse me, you're going to bring the 10 out front, and then you have 10 times 1, 30 of 30. Here, you bring the -12 out front, and then E of E gives you 1, so your answer is -12. This one, okay. Once again, you've got the 10 of this, so it equals the 14 because there's a hidden base 10 on this log right here. Here, you've got 8 of 8, so the power is your solution. Graphs of logarithms, okay. We didn't do much of this on the test. You can make yourself an XY table and graph it. This one is a transformed one. In other words, we're going to shift left 1, and we're also going to go up 2 compared to this. What this problem is wanting you to do is recognize that these two go across that y equals x reflection. And then also they want you to recognize that the domain of the first one is the range of the inverse, because remember, this and that are inverses. These two are inverses. This could also be written as x equals b to the y. This could be written as x equals b to the y as well. We continue. Here's some domain of this one. Becomes the, notice this range and this domain, okay? And this VA they're talking about is the vertical asymptote. There's a limiter on this one of -3 that it can't cross that -3. On this one, it's saying there's a limiter of 0, which is the y-axis here, okay? What is the domain of this? In other words, it goes from here that way. This thing, you've got two answers, so you end up with two graphs, okay? The range is from -infinity up to forever, okay? The domain, you've got from here to there, union here to there. And again, there won't be one like that on the test. This number 33, you did not have to work. Now we begin with problems that are similar, starting with number 21 on your test Wednesday. Okay, for this, we're going to expand it. 2 plus log of x plus log of y. Here, we're going to expand this. Log base 2 of 2, log base 2 of x, log base 2 of y. Notice the process is the same, whether it's base 10 hidden here or whether it's base 2 exposed. Here we're using natural logs. First thing we do is we take log of 3, and then we take log of the entire parentheses. Okay. In this case, this is actually a problem similar to number 22 on your test, where you have to use the division rule. So because this 49 is in the denominator, we have to subtract that log of 7, 49. The 14's in the denominator, so we have to subtract the log 7 of 14. Because the whole x plus y is in the denominator, we have to subtract the whole x plus y behind the log. Okay, number 7, using the power rule, you'll have to use this process in some of your problems as you go. Okay, it's not a separate problem into itself, but it's a step in several problems. So in this case, you bring the 5 out front, so you have 5 natural log x. You're going to bring the 5 out front, natural log of e, but natural log of e is 1, so your ultimate answer is just 5. And you'll be expected, if you have something like this, to do that simplification. If you've got a radical one, then you have to change it to a fractional power, bring the fraction out front. Okay. More of these expansion problems. You got a log of 5, log 3 of z. Then because the w is in the denominator, minus log 3 of w. Here we're going to add the a and the c's. And then we're going to subtract the 5 and the D. Here we're going to add the x's, x squareds, and the y's. And then we have to bring the 2 out front, so we get 2 natural log of x plus natural log of y. And this would have been the same whether it was standard log or natural log. This one we went over in class. By the way, all of these problems we went over in class. So you can look back at your notes for those also. We changed this radical to a fractional exponent. So x to the 2/3. Remember, the root is always the denominator on the fractional power, minus the entire w plus z. We bring the 2/3 out front, minus that, and that's as far as we can go. Okay, on this one, we get rid of the power here, we bring it out front. Then we deal with expanding this 4x plus that, all behind that 1/2 we brought out front. Okay, so we've got that, which this ultimately will simplify because 4 is the second power of 2. We got this minus the y minus the z cubed, and we'll have to bring the z cubed out front. Then we're distributing this y, or this 1/2, excuse me. 1/2 times 2, 1/2 times that, 1/2 times that, and 1/2 times this 3 brought out front. You're actually not going to have any problems quite as difficult as that one on the test. Likewise on this one, similarly, okay, we've got to get this x squared brought out front right here. 64 is the second power of 2, so we have to simplify that and bring the 3 out front here. Expressed as a single log, we're contracting because it's subtraction. We put that log x, that x in the denominator of the log. Here, we've got a plus, so everything is going to be multiplied. The z, bring the 4 back out here, so y to the 4th. In this case, we've got 2 terms multiplied in the numerator. First, we bring the 3 out behind the x, and then the 5 in the denominator. And you can see number 19. Again, we're not going to have any as difficult quite as these right here. This minus right here is going to force us to put that all in the denominator. Here are more computer problems, okay? It gives you some substitutions. You're not going to really have a problem like that. Your change of base formula on that problem, when you do it, I expect you to write this first like this. Since it says in terms of E, then you'll put an E right here, and then later you'll convert it to natural log with whatever numbers values it has for the X and Y. Okay, here's an example. This one is very close to your problem, except you do not change it to a numerical value. In this case, if it were standard logs, you would go this way and this way. Notice the 3 in the numerator, the 5 in the denominator. This would be your answer if this were the test problem. And again, you don't take it to numerical because I'm testing to see if you know how to use the change of base formula. Now we go to equations. And am I past time? Oh, I apologize. I'm past time. I'll let you look at these real quick. I'm going to go ahead and continue. And we will not have online class tomorrow. Well, yes, we will. We'll take up right here tomorrow. We're going to have online class tomorrow, but it won't be the full length of class. I suppose partly to make up for today and partly because we're not going to need it all. So with that, I'm going to get out of the share. And if any of you have any questions, you're welcome to ask them or write me chats. Otherwise, we're done for today. And I apologize for carrying on over time. Nothing? Okay. See you tomorrow.
You can choose to wait and pay it off in one lump sum when you read it. No obligation to reach mortgage loan. Access tax-free cash and save.
Good morning. Today, what we're going to do is we're going to finish doing the review for the material over Chapter 4, and then we will actually begin Chapter 5 today, the last half of class. When we will get as much done as we can today on the introductory part of Chapter 5, then on, of course, tomorrow you'll take your test. You may begin at 11 instead of 11:10, but we may have to stop 5 minutes earlier than usual. On Thursday, we'll go over the test as usual, and we will finish the material for this week out of Chapter 5. So there will not be class on Friday. You've got a day off. When I agreed to teach this class, I told them there were a number of Fridays throughout the semester that I would not be able to be available for teaching the class, and this happens to be one of them. So again, there will not be class on Friday. We lost someone. Uh-oh, they're back. There will not be class Friday at all. We will cover Chapter 5 material today and tomorrow and Thursday. Okay, with that, let's go ahead and get started into the material. Whoops, wrong one. Okay, there we go. This is where we left off at section 4.5 yesterday. We're dealing with solving exponential equations. If you have an equation which has a base, compatible bases, then you want to use that trick. Here you have the same base, so you just simply get 3x minus 1 equals 3, and you solve that equation. In this case, 8 is a power of 2 to 1 or 4, and 1/4 is a power of 8. In other words, 8 is 2 to the third, 1/4 is 2 to the negative second. So now we have the same base. We combine the 3 and the x over here. So 2 to the negative second equals 3 to the x. We remove both bases, and we have -2 equals 3x and finish solving. For those who just came in, I'll reiterate, there will be no class Friday. Today and Thursday, we will cover the material on Alex for this week out of Chapter 5. Okay, on this one, again, we've got a base 2 to the third and a base 2 to the second. So we replace those. We simplify the exponents, remove the 2 bases, and we've got 7x equals 1, x equals 1/7. This time we do not have compatible bases. Your strategy when you don't have compatible bases is you take either log both sides or natural log on both sides. It doesn't matter whether you use log or natural log most of the time, unless there's an e in it, in which case you would definitely want to use natural log. Okay, we use the power rule to bring the x out front. Okay, then after that, we divide both sides by log base 2. And in your calculator, then you convert it to a decimal if that is requested. Otherwise, you could leave it as log base 7 over log 2. another set of incompatible bases. So we take natural log of both sides. We could have taken regular little log if we had chosen. It really wouldn't matter on this problem. Okay, so using the power rule, we bring this negative 0.02x out front. Then natural log equals this. Then we're going to divide both sides by natural log 3. And also we're going to divide by the negative 0.02, okay, leaving the x on the left. You have these two you can put into the calculator and then get that answer. I'm not going to actually use the calculator today because of the problems we had yesterday with the stalling on this Word document that I've got open. You've seen me use the calculator to enter those logarithms and divide them and such before. Okay, here once again, now we've got the added factor of having this 4 up here as well as the exponential value. So first thing we do is move the 4 to the other side with the real numbers. Then we're going to divide both sides by 3. Now we've got our simple exponential value and real numbers on the other side. Because this is an e, we're going to take natural log on both sides, bring the 2x out front, and natural log e is 1. So 2x times 1 is 2x. And then over here we've got this. Instead of dividing both sides by 1/2 and getting a complex fraction, we'll just instead of dividing both sides by 2 and getting a complex fraction, we'll multiply both sides times 1/2. 1/2 times 2 is x, and 1/2 times all of this is that. This is a number you can put into the calculator and get your answer. Okay, and number 7, we have incompatible bases. So we're going to take log on both sides. First, we're going to bring the powers out front. Okay, then we're going to get all of the x terms on one side and here's the x terms on one side after we've distributed this, distributed that, and get the non-x terms on the other side. We factor out the x's, then divide both sides by this 3 log 2 minus 2 log 3. You end up looking like that, and you can put it in the calculator. It's not required for us to do one of those as part of the curriculum. We do have to solve logarithmic equations, okay? If we look at the difference in these two equations, here I have logs in all terms. Here I have real numbers as a unique term. So that's the difference, and we deal with these in a slightly different, well, a majorly different way. The ones where we have logs in all terms, we'll simplify the logs and then remove the log of the same base on both sides. The ones with the real numbers in them, what we'll end up doing is converting logarithm to exponents to solve it. Okay, here we go. We've got all logarithms. In this case, we can remove logarithm of 2 on both sides, leaving the simple equation to solve. Over here, again, we can remove log on both sides, and we can solve it. However, if we put this 6 in here, then we would get a negative value, a negative log of -1 in this case. So it is undefined and no solution. We didn't check this one over here, but if we put an X in here, I mean a 6 in here, we're going to get a positive value. If we put a 6 in there, we'll get a positive value. On number 11, we've got this. Okay, remove log on both sides, leaves us this rational problem. Multiply both sides by x plus 1. When we do here, that cancels the 1 in the denominator. Over here, we distribute it. Solve this equation, we get x equals 6. In no cases, if we replace the x with a 6, will we have a negative log. Okay, on this one, we first simplify this using the multiplication rule backwards. Since I've got this plus, then I take the log of this x times the log of this parentheses and the natural log 10. So now I have a single natural log on both sides. You can't remove it when there are multiple logs on one side. It has to be a single log on one side. Okay, given that, we multiply these. We've got the 10. We bring the 10 over. We solve this quadratic by factoring, and we get these two values. But when we attempt to put -5 in for the log value here, we would get a negative value, a negative log. So we have to throw out the -5. Number 13, we've got multiple logs on one side and a single log on the other side. So as it is right now, we can't remove logs on both sides. So let's simplify this side. We've got log 3 both places. So we're going to have 2 times 3x minus 4 using the multiplication property. Now we have a single log both sides, so we can remove it. That gives us x squared equals 6x minus 8. Bring the 6x and the 8 over to the left, factor it, and we get these two values. We check both solutions everywhere in the original, and we're okay, so both solutions check. Okay, now we're talking about where we have a constant or a real number in the problem, as well as a log in the problem. This, what we're going to have to do in this case, we're going to convert this log, treating this whole parentheses as if it were one value. We're going to convert this from logarithmic to exponential. The base remains the same of 5. The 2 becomes the power. And then the 3x plus 1, your argument becomes your solution. Well, we square 5, get 25. We have a simple equation to solve. Now, we should check this to see if we replace the x with 8, if we would get a negative value. We don't, so we're okay. Over here, I have 2 log terms. I have to simplify that to a single logarithm. They're both base 3, so I can use the division property to simplify this expression. That gives me the x plus 6 over the x minus 2, all log base of 3. Now we're going to take this log base of 3 equals 2, and we're going to convert it to exponential. The base remains the same. Here's the power. Here's the solution or the argument. Okay. 3 squared is 9. multiply both sides by x minus 2. Over here, when you multiply this by x minus 2, the x minus 2's cancel. Over here, we distribute 9 times x minus 2. Gives us an equation to solve. We get the x's on one side, the numbers on the other side, and we discover that x equals 3. We check it, works okay here, works okay there. So our answer is good. Okay, in this case, remember that a log without a base is automatically base 10. That'll become important when we convert this to exponential. Now, we've got logs on both sides. So first thing we do, let's take this minus log x over to the left side. So it gives us the plus log x here. Now we're going to use the multiplication rule. So we've got log of x times x plus 15. The order does not matter on this x and this x plus 15. Now, in this case, this whole thing, x times x plus 15, is your argument. Will come down. The log base 10 stays the base to the second power. I multiply this, take the 100 to the other side. It factors and you get negative 20 and positive 5. We have to check it. If we put negative 20 in here, it won't work. If we put negative 20 here, it won't work either. So we have to discard the answer negative 20. And the 5 does work both places, so we're good there. On number 17, again, we've got a mix of logs and real numbers. So we get the logs all on one side, the real number on the other side. Then we're going to use the division rule to take the x squared minus 9 over the x plus 3. We use the we convert to exponential. Base is 4, power is 3, and here is the argument. Now, x squared minus 9 factors into x minus 3, x plus 3. And the x plus 3's cancel. So we've got x minus 3 equals 64, because 4 to the third, 64. Add 3 on both sides, and we get x equals 67. Okay, applications. Here is your growth formula. It's also the constant interest. It's the constant interest formula. They are one and the same. Okay, in this case, you got an investment or P of 20,000. The interest 0.025 when you change it to a decimal. And it wants to know how long will it take for the total amount to be that. So in other words, they've given you everything except the time. We put in the 4,500, the 20,000, E, the interest rate times time. Well, first thing we're going to do is we're going to get rid of this 20,000. So we're going to divide both sides by 20,000. And when we do, 20,000 goes into 45,000 2.25 times, or 2 1/4 times. So now we have an exponential form. We're going to take this exponential form and we're going to convert it to logarithmic. Okay. Now I could have written standard log base E of E to this. Now, what we're going to do is we're going to use natural log on this. Okay. So My base is log of E or natural log, okay? And then here of 225 equals this. Now, with that, what we're going to do next is we're going to divide both sides. We want to isolate the t. So we've got to divide both sides by this 0.025. And we do that. And in the calculator, it comes to that. And because we're talking how many years, whole years, it would have to round up to 33 years. Okay, we're not going to do a problem 19. Exponential growth, positive. Okay. In other words, if you see here, this is basically the A equals P sub O e to the RT, same as that. For exponential growth, the rate K is positive. For exponential decay or diminishing money, K would be negative. Okay. In this case, it says you got $1 million you want to have when you retire. You play 100,000 in the lottery. So that's your starting, is your 100,000. The ending is $1 million. Now, for the time, you want to retire at age 67. You're 19 now. 67 minus 19 is 48 years. Now, continuous compounding, here's the formula we're going to use. A equals PE to the RT. So in this case, the A is $1 million. The P is 100,000. The time is 48, and we don't know the rate. Okay. 100,000 goes into $1 million 10 times. So we simplify this. This is an exponential problem, so we convert it to logarithmic. So log base E of 10 equals 48R. Divide both sides by 48. So you put the natural log of 10 in your calculator divided by 48, and you come out, you need an interest rate of 4.8%, which is not an interest rate you would get right at this time and place.